We've been looking at a bunch of stuff involving momentum and conservation of momentum and things hitting each other and stuff like that. And the same underlying principles applied every time, where momentum before has to equal momentum after. Well, we're going to look at a slightly different situation that still follows the exact same rules. And here we have a sphere, a big red sphere right here, and this yellow vector here, that's its momentum. And you got the green one here. This guy's a little bit smaller. He's just sitting there doing absolutely nothing. And the red one is going to bonk into the green one, and they are going to move off in different directions. So this is like another collision situation, except instead of hitting like in a straight line, it's actually going to hit at an angle. So if we actually bring the red one in, we can see it hit it, and they go off something like this. So you can sort of think about playing pool, or like a curling rocks would be a perfect example of something like this, where things often hit each other and go off in different directions. And you see the yellow vector here for the red one has changed, and all of a sudden the green one has a momentum vector as well. And of course, that momentum came from the red one. Now, you might think that if you took these two arrows and just add them together, if this was 2 and this was 3, that the other one started with 5, just adding them together like that. Well, it doesn't work that way because they are vector quantities. You have to take their direction into consideration. So let's go back again. Let's have a go again. So the red one comes in, they bonk, and off they go. Okay, so we're going to look at a situation like this a little bit, sort of expand and push your knowledge on this stuff a little bit. And so you can sort of see it doesn't matter the situation, it doesn't matter how things lay out. Before equals after. It makes no difference in this scenario for conserving momentum and stuff like that. Okay, so what we're going to do is we're going to adjust this a little bit and look at some screenshots of what's going on, and I can show you a couple things. So here we have a couple screenshots of the animation I just showed you, and here we have the initial situation where they arrest, and then this is afterwards when they were moving off after the collision. So this yellow vector here was, of course, the momentum before, and these two vectors here represent momentum afterwards. And whether you're in a straight line at an angle doesn't make a difference. Momentum before is supposed to equal momentum afterwards. So what I'm going to do is I'm going to take this vector right here. I'm just going to try and just chop it out as best I can. And I'm going to move it over here. And if I do the same thing with this vector right here, and I move it over here, you can see that those two vectors added together still give you the exact same thing as the vector that we started with, because momentum before has to be equal to momentum afterwards. Okay, now if I get rid of them and put them back, there we go. If we sort of did this a little bit differently, this vector here is going straight to the right. That's what I started with. That was my initial momentum. Everything was going straight to the right. I didn't have anything going up and down. Well, these guys are both going up and down and to the right. Well, before has to equal afterwards. I can't have something afterwards that I didn't have before, which means if I didn't have anything going up and down at the beginning, I can't have anything going up and down at the end when they're put together, which means whatever this one has going up, this one has to have going down. Okay, now this one had momentum to the right. Well, these both have momentum to the right, and if you take the amount this one has to the right and this one has to the right, they would actually combine together to give you what this one is. So let's sort of just make up some numbers here and see what's going on here. Okay. So, for example, suppose the momentum for this guy here was 5. Maybe it was 5. I'll get a little bit thicker. Maybe we had 5 for momentum going towards the right. Well, this one is going towards the right, and this one is also going to the right. Well, maybe I knew this one had a value of 2. Well, if this has a value of 2 going to the right, I know this one has to have a value of 3 to the right. So the 2 and the 3 will add up to the 5 that I started with. And connected to that, this one's going up and this one's going down. And maybe this one is going up with 1. Well, then I know this one will have to go down with 1. So the 1 up and the 1 down will cancel out. and give me 0 in the vertical direction, just like we have over here. We don't have anything in the vertical direction. Okay, so if I sort of piece this all together, let's say, let's use a balloon here. All right, let's say this represents my total momentum, that vector right there, that's my total momentum. This one here, this is the momentum of number 1, and this is momentum of number 2. Each one of these can be broken apart. There's momentum for 1 in the x direction, and there's momentum for number 1 in the y direction. And we just made up numbers here, that doesn't matter. What I had here was 3 in the x direction and minus 1 in the y direction. I'm saying it's minus because it's going down. For this one, we have momentum 2 in the x direction, and we have momentum 2 in the y direction. And in the x direction, we had 2, and here we had 1. So it's 2 to the right, and then 1 up. 3 to the right, 1 down. And if we just sort of piece things together, our 2 y components have to cancel off. If you don't start with anything in the y, you can't end with anything in the y. So these 2 have to cancel off because we didn't have any y momentum here. On the other hand, we have our 2 x values, 2 and 3. Those 2 x values have to add up to 5 because that's what we had at the beginning. We had x momentum at the beginning, we have to have x momentum at the end, and they have to be equal to each other. Okay, so it's the same idea as before. Momentum before equals momentum afterwards. But sometimes when things go off at angles, you have to look to make sure that whatever's going sideways stays the same, and whatever goes up and down stays the same before and after. So now let's just try an example, just to show you how this works with a couple curling rocks here. Now curling rocks are supposed to be the same size, but we'll just using them as an example here. So here we got a 3 kilogram curling rock, and let's say this curling rock is traveling straight to the right. Let's have it coming in at, let's go to 6.0 meters per second. And then it's going to, of course, hit this curling rock over here, and this one's going to go down this way, and obviously, more than likely, this red one would then come and shift off this way. Okay, so let's say that curling rock's coming in at 6 meters per second, and let's say this rock over here goes this way, and let's say it's going at, let's go with 8 meters per second, something like that. And let's say we got a little angle here. Let's say this is a 50-degree angle, something like that. Now what we're going to do is we're going to try and find out what is the momentum of the red rock afterwards. So we're going to find that momentum of the red rock afterwards, find out which way it's actually going. Well, just like we were talking about before has to equal after. So why not start with before? So I'm going to find my initial momentum with this with my red rock, and that's going to be my initial momentum I'm starting with. So I've got the 3 for the mass, I've got the 6 for the v. I put the 2 together, and you've got 18 kilogram meters per second. Okay, so that is the momentum that I have going into the situation. Now, that is the momentum before, which means that has to be the momentum afterwards. That cannot change. So whatever I got the 18 before, I have to have 18 afterwards. So let's see what I have over here with this rock. I can work with this rock over here and find out how much momentum it has. So momentum of the yellow rock is going to be mass of the yellow times the velocity of the yellow. So I've got the 1.2 and I've got the 8. So 1.2 times 8 gives me 9.6 kilogram meters per second. Now I can't just subtract the 2 because it's going off an angle. I need to break this thing apart into x and y components. So this little yellow rock has got momentum in the x direction and has momentum in the y direction. So I'm just going to use my basic trig to figure out those components. So I got momentum for the yellow rock in the x, I'm going to have momentum for the yellow rock in the y direction. So I got the 50 degrees, so I can use my cos and my sine in order to figure out what those 2 momentums would be. So let's see, doing our basic trig, we have about 6.2 going towards the right, and we've got about 7.4 going down. And we'll just round it off a little bit. All right, so those are the two sides of my triangle. So now I can use that to help me figure out what's going on with my red rock when it's out here. Because my red rock also has two components, a vertical component and a horizontal component, and I can sort of try and piece things together. Well, first things first, if I don't start with any y momentum, I can't end with y momentum. So if my yellow rock has got 7.4 going down, I know my red rock must have had 7.4 going up to cancel it off. And I know my x's have to add up to what I started with because that's all I had at the beginning. So I started with 18 in the x. So far, I've got 6.2 in the x. Well, I've got 6.2, but I need 18. All I have to do is subtract the 2 to figure out how much I'm missing. And 18 take away 6.2 would give me 11.8. So my two x components, my 11.8 and my 6.2, those will add up to the 18 that I started with. So I know that my red rock afterwards has 11.8 sideways and 7.4 going up. So now I can use Pythagoras to figure out the hypotenuse, how much momentum it actually has, and then trig to find the angle. So Pythagoras, let's see, so momentum for the red rock afterwards. Using Pythagoras to find the hypotenuse, we're looking at around 14 kilogram meters per second for the momentum. Then we use some trig, using tan theta would work really nicely, and we get an angle of around 32 degrees. So that would be the momentum of the rock afterwards. And then what you could do is you could actually take this and divide it by the 3, and then you'd actually have the velocity of the rock afterwards. So again, very similar to what you guys done before, like momentum before equals momentum afterwards. But this one, you just got to look at the different vertical and horizontal components separately and make sure they add and subtract to what they need to. So now let me show you what this sort of looks like in an actual situation. Here we have a guy playing pool, and he's going to do a trick shot where he's going to shoot that ball, and he's going to hit these 6 balls right there. And if you actually watch what's going on, it's very similar to what we were just talking about with conservation of momentum. If we actually watch the shot, we'll give you a little show here, and you can see what actually happens. All right, so as you can see, when he hit the balls, the 6 balls all went into the 6 pockets. Now, if we actually back this up a little bit, we can actually see a little bit what we're talking about in terms of momentum. So here's the same thing, except we have a little lines showing where those 6 balls are going to go after they collide. Notice how symmetrical they are going up and down. Every time something goes up, there's something going down, which cancels off momentum. When that cue ball comes in, it's coming straight from the left, it's going straight to the right. It has no up and down momentum. Therefore, the 6 balls afterwards also have no up and down momentum when you put it all together. Also notice that there's generally more lines going towards the right than there are towards the left. That's because when the cue ball came in, it had momentum towards the right, which means we have to totally have some momentum towards the right afterwards. So the left and right stuff can't cancel. We do actually have a little momentum going backwards to the left, but then the system actually compensates by having even more towards the right. So if you would actually take all 6 vertical momentums of those balls and put them together, they'd all add to 0. And if you would take the horizontal momentums of those 6 balls afterwards and you add them together, they would actually add up to exactly what the cue ball came in with to be at the very start of the shot.